Welcome back everyone. So, we are studying topological phases of matter and this is the second lecture. So, in the first lecture we looked into a particular geometry in which we confined our magnetic field in a solenoid. So, magnetic field is finite inside and magnetic field is 0 outside. And then we had an electron, it is a quantum mechanical electron which is circling around that field, around that solenoid. So, it sees the vector potential, but not the magnetic field. So, at this point the magnetic field is 0, but then it sees the effect of the vector potential as a connection because it is traversing in a manifold which has a hole, right. And what we have found is that the phase that electron acquires after completing a loop, the phase it acquires is quantized to 2 pi n because it is a single valued wave function fiber, and that phase turns out to be equal to the flux that is encircled in this loop. Obviously, the flux is not spread over the entire loop, it is only confined within this region. So, even if you make this loop smaller and smaller and larger, your flux remains same and the phase remains same. So, it is a quantized condition. So, that means because the phase cannot change, cannot take any value, the phase in this entire loop after coming back cannot change by any arbitrary value, it has to change by 2 pi n. So, then it sees the flux not as a continuous variable, it sees the flux as the flux can only change integer value such that the corresponding phase can change integer value. So, for any other continuous change of the flux from some integer value to another integer value, the electron sort of becomes indifferent to the change of flux until the flux changes by integer value, and that is the topological invariant, right. It does not change any continuous value, it only changes because what we are doing is that as you are changing the flux through it, you are sort of either changing the topology if you like, and or you are changing the size of the loop or the winding around that flux. Both are sort of equivalent way to say it. And another thing we learned is that in this geometry the electron look at the magnetic field as a diverging field. It just comes mathematically. So, it is the magnetic field is 1 over r square times the integer multiple of flux quanta, and that flux quanta we define as a monopole charge, right, and we define the monopole charge as the flux quanta integer times the flux quanta. So, then what we have done is that we sort of elevated this problem to saying that this is where my magnetic solenoid which is there, which was there, and we sort of squeeze it to a single point, and the electron which was making a loop in 2D. Now, we sort of assume that this is happening at the equator of a higher dimensional space R3, and rather we are interested in S2. Okay. So, the vector potential which was there on these 2 dimensions, which was this quantity, now we add one more variable theta, and this is along the phi directions, right, and this theta is an answers that we put. Then we see that as you elevate to this direction or S2, we see that we really cannot define a smooth gauge field over this entire S2. So, there has to be at least 2 charts, and in one chart it is smoothly defined in the north pole, but not at south pole, and the other one, another chart, the vector potential is smooth in the south pole but not at the north pole. So, another way to say is that there is, from the north pole perspective, there is a solenoid that has passed through the south pole, and to bring a monopole here, to create a monopole at this point, and from the south pole's perspective, from the charts of the south pole's perspective, the monopole charge is put to the center through the north pole. Okay. So, that is a way to think about it, but mathematically this is equivalent to having a monopole charge as at the center. So, monopole charge can be stabilized only with a topology which does not have a smooth gauge, but there is a gauge obstruction. There has to be at least 2 charts. So, it has to be a non-trivial topological space. And we said that also that each gauge fields are arbitrary by the change in by some change of the scalar field or potential, but the difference is a gauge invariant quantity, and that should be very easy to check, and you will see that that depends on that change in the gauge field is the gauge field that we obtained and the equator in the previous chapter. That is the monopole charge. Now, we will take it to the next level, and we will define now quantum Hall effect. Okay. In fact, before I do that, let me also show you that I advertised earlier about what is the. So, these are kind of a cyclotron orbit, if you like, this or even the one that we talked about earlier in 2 dimension right here. So, the single valuedness is protected by some conjugate quantity, right, and so it is a homework for you to figure out that it is not the angular momentum of the particle that is conserved here, but angular momentum times the monopole charge or the flux that is passing through. Okay. As you increase the flux, it adjusts with the angular momentum to get a single valuedness. Okay. Show. And so, it is kind of a mathematical quantity in which there is a electric charge and a magnetic charge sitting together. So, it is a quantity which has both electric charge and magnetic charge. So, it is called ion. Okay. There are some claim that it has been observed, but not conclusively. All right. So, now we move on to quantum Hall effect. So, now we are doing this, the sort of setup that we talked about, but in a uniform magnetic field, and okay, let me show you the geometry. Okay. So, this is my kind of a 2-dimensional Hall bar, right, with some length Ly and Lx, and we add a current or voltage difference in the x direction and a magnetic field that is perpendicular to this. Some magnetic field which is there everywhere. Okay. So, electrons without a magnetic field are supposed to be going from along the x direction, but now with magnetic field, because of the Lorentz force, it deflects. So, it goes to the A. So, electrons will go to this side and the hole will go to this side because of the Lorentz force and the centrifugal force that it obtained. And I will tell you, so this is the magnetic length which I will describe, and so maybe I will describe here. Okay. So this is the radius of the electron, Lc is equal to minus E V cross B. Okay. So with that we can figure out that Lc is equal to the magnetic length. Alright. So this is the radius that it makes. Now if this radius becomes comparable or larger than the size of the sample, which will happen at low magnetic field, then you will see that the electrons are just going to the other side, and then the voltage, which is called Hall voltage, it will create a voltage difference between this side and this side, because electrons has gone there and holes are going here, and that is the Hall voltage. And you will see that this Hall voltage will increase continuously as the magnetic field increases. More electrons will be going there. But as you increase the magnetic field more and more, and then this radius decreases, you will see that once the Lc becomes smaller than Ly, or the length scale of the system, you see that it starts making cyclotron orbit with some magnetic flux that is inside, which is kind of confined in a, and this is the physics we just studied earlier. So it will keep on rotating here, so it will be localized. They will not be moving yet to this side. And in this case what happened is that the ones at the edge, so this is kind of a semi-classical picture, and we will quantify it with a more quantum mechanical picture, is that once these cyclotron orbits are drifted towards the edge by electric field, they will not be able to make a full circle, but they will make half circle, and then they will have a velocity along the x direction. These are called skipping orbit. And in this region, so it is kind of a conducting channel. So one channel, and then as you increase the magnetic field, then, or initially there will be many channels, and as we increase the magnetic field, the number of channels will get reduced. They will become more localized because they are getting smaller and smaller, right? And eventually there will be only one of them, which is what will be the case when there is only one Landau level element field, and these are the one that creates the current, and you will still have a voltage difference because these are the electrons skipping orbit and this is the hole skipping orbit, and in this region the Hall effect will be quantized. Alright. So let us understand this, where does it come from. Okay. And the one that I didn't define is called Hall resistance or transverse resistance. Well, this is the Hall resistivity, resistance, and these are the Hall resistivity times some area or length. That is by definition V is Hall voltage divided by Ix, right? Or if you like, it is the voltage difference along y directions and due to current along x direction. Alright, so that is what this tensor stands for. Alright, and dimensionally that is like inverse of conductivity, but of course the relations are not that simple, and as we will see, because these are a tensor. So, if I just do a semi-classical treatment which is like Drude model, we do expect the conductivity in the Drude model, the carrier density with charge and mass of the electron times the relaxation time, kind of a time scale by which the electron sort of disappears from some momentum state and goes to another momentum state, the scattering time scale, or inverse to the mean field length. Okay. So, with that, and we also defined mobility, in which we will have n e mu, where mu would be defined as, so it is a characteristic of a material telling us how clean the material is. It depends on the mass, and these are the fundamental numbers, and this is the time scale. So, the cleaner the sample is, the mobility is higher. So, now if you do this kind of back of the envelope calculations, if you like, the longitudinal conductivity would be and the transverse one all right, and the corresponding resistivity you can work it out. Saying that this one is linearly proportional to or linear with magnetic field, whereas this one does not depend on magnetic field. So, if I make a plot, this should be linear. This is what one would expect semi-classically. Okay. So, what happened is that initially that is what happened experimentally, and then start changing, and initially also it start happening like this up to certain value, which called classical region, all right, and let me show you the result. And this is the result which I will redraw there. So, this is what the longitudinal one, it is like a classical, and then it start oscillating, and then it vanishes, and then has peak and vanishes, and then has peak. Whereas the Hall resistivity, it was again going like a linear initially, which is the classical one, then steps starts to form, and these are the regions which are the precise quantum region, precise integer multiple with the resistivity quanta, and which is E times the inverse of flux quanta. Okay. So, initially it will go like this. It starts forming steps with some around this classical value, whereas this guy will go like this and start forming. So, I think I will be careful from this point, or maybe let me do this. Right, so, in this region wherever the step is changing, it's sort of drawn in arbitrary scale, two of them. Okay. All right. So, you start seeing some oscillation before it vanishes and then start having peaks, very sharp peaks, and the peaks are going to happen where the experimental behavior, and these are rho xy, the experiment, whereas these lines correspond to what we expect from the semi classical theory. Okay. And something up to this region we can call it, these are called Subnikov D has 1 alpha oscillations. This is a name, you must have seen it in condensed matter 1 course, and they are given by the name Subnikov and Dihas 1 alpha, and they saw the oscillations in the resistivity, okay, and we will call it rather quantum oscillation, whereas this region we will call it integer quantum Hall effect. So, what happened is that 1, 2, 3, 4 and so on. All right. So, how come they become precisely quantized to a value 1, 2, 3 modulo some fundamental constant? So, they do not depend on any other details of the system, and whether this is iron or copper or any other material. No material properties are here in these values, they are precisely 1. This is the integer quantum Hall effect. Okay. So, a semi classical model definitely failed, and by this time we already knew that the under a magnetic field, and the problem that we solved in the first lecture of this chapter 2 was through this parallel transport, and if you go ahead and solve it with some sort of a gauge, Landau gauge, then we see that the cyclotron orbit are kind of a harmonic oscillator. So, that means the energies are quantized for each level, and I am not going to solve it, but you should look it up if you have forgotten. quantized with energy level spacing, that is called cyclotron frequency. Alright, and n being integer. Alright, so any sort of a dispersion or complicated energy, whatever the dispersion the system had before you apply the magnetic field, and all these dispersions with energy as a function of momentum and so on will just become flat with energy levels like this. Okay, n equal to 1, n equal to 2, like the harmonic oscillator, and this is the energy. And so that means in a given band there are many states, so and it could accommodate many electrons having a different momentum value. So all those states will now collapse into one state. So that means this should have a lot of degeneracy, and you can work it out, the degeneracy to be the area of the sample, which is Lx Ly in this example, E B. So the degeneracy increases so this is the flux. So it is the flux, total flux that is passing through this entire sample divided by the flux quanta. Okay, that is what the degeneracy is, and as the magnetic field increases, the degeneracy increases. So now what is happening here is that so now let us draw this so these are the resistivity as a function of magnetic field, and as a function of magnetic field we have just drawn these energy levels. So this is our energy Landau levels, and as it is okay now as a function of B, and since E n is equal to 1 plus half h omega b omega c, the cyclotron frequency, and this is proportional to B. So as the magnetic field increases, the separation between the Landau levels increases. So initially for small fields, the Landau level spacing was very close to each other. So it is like these energies are like a continuum of energy. The separation between those energies is too small to be able to visualize experimentally. The systems are also not very clean and all, right. So and we'll talk about that here. So you do see a continuum of energy, and that is what you see a classical like behavior in the resistivity. Okay, it is sort of blown out here. This is the classical region. So now as you come to the intermediate region, this was the classical region, and this is the quantum oscillation region, right. So there is not a sharp transition from classical region to quantum region, but it is more of a material dependent. So what happened is that this Landau level spacings are there, but whether you can distinguish them or well or not, that depends on how clean the sample is, and so that depends on the mobility of your sample, and that roughly gives you the broadening. So this also gives you roughly the broadening of this state of these Landau levels, and also that will end up in the density of state. So, if I draw a density of state around this, so you see that now the density of state has this broadening associated with this quantity, and this is the density of state associated with this, okay, and this broadening is proportional to some the inverse proportional to the lambda rather. So, it's okay. So, now you see that these two density of state overlaps, but there is still a dip as we go between the two Landau level. So, you have a oscillations in the density of state. Okay, and then here the density of state was flat, and here you see the oscillations, and this is the oscillation that ends up in the oscillations in the resistivity or in the carrier density. Alright. And that is the oscillation that we measure and call quantum oscillations. We measure it through resistivity or through magnetization, okay. And I can probably exaggerate it a little bit. I hope it is clear. Okay. Some oscillations in the resistivity, or maybe I will erase and now I will draw cleanly. Okay. So, if I draw the density of state, now what happened is that we come to a region where the density of state are only peaked around a Landau level, or I can draw it here, and the width still is inversely proportional to this. And this density of state are well separated now, okay, and that will give you the peaks in the longitudinal resistivity. On the other hand, in the transverse one, there will be a jump from one Landau levels to another Landau level, but as long as we are between two Landau levels, it only counts how many Landau levels are filled. Okay. And here you at the last one you will have only one Landau level that will be filled, and here it will be two Landau levels, three Landau levels, and so on. And that gives us the quantum Hall effect. So, quantum Hall effect does not mean that it is a quantum effect and this part was classical effect. So, it is not that, it is the quantized Hall effect, that is what we call quantum Hall effect. This part is also quantum effect, this part is also quantum effect, which we approximate as a semi-classical one, but all of them are quantum effect. Okay. So, you can even go back to the classical, the semi-classical approximation, and you can show that because the expressions I wrote earlier was this, that or yy equal to sigma t divided by 1 plus mu p. And now we are in some sort of a clean limit. So, clean limit means goes to infinity, and so this means mu goes to infinity. Clean limit means the system has not become clean as you increase magnetic field, but now we are at a large magnetic field region where the Landau level spacing is much larger. So, from the Landau level spacing perspective, the system is clean, so that is why you can take this sort of limit mathematically. These things do not matter, or the inverse of tau is 0 compared to the broadening or to the spacing between the Landau levels. Okay. So, if you do that, we get rho 6 to be equal to 0, and if you do the yx and if we substitute all these values, we will get that is equal to in this limit we will get the Drude conductivities divided by cyclotron orbit. Yeah, so I think this is not there. So, it depends on the carrier density, and the carrier density we can just compute. So, each label has this many electrons, this is the density of state, and then the density of state is nothing but the delta function for energy minus this Landau levels. Okay. And sum over Landau levels. How many Landau levels we have filled it? Right. Minus infinity to Fermi level. And this one is equal to, just put all these values that you have it in the previous note, times the number of Landau levels that is filled, and this is an integer. Okay. Which tells us that is equal to, we substitute all these things here and we substitute n equal to this, and you cancel all the, and you also substitute for this, you will find this is equal to n square. It is just count how many Landau levels are filled. So, it becomes completely integer times this value. Okay. So, we are seeing this quantum Hall effect as just the Landau quantizations, and now we will start talking about what is the topology, how the topology enters into this phenomena, and that we will do in the next class. So, thank you for your attention.